So let's read this one.
Power Jets Woo. The Power Jets Woo Whittle unit was a series of 3 very different experimental jet engines produced and tested by Frank Whittle and his small team in the late 1930s. Design and development, edit. The Woo first model, also known by Whittle as the first experimental engine, and the first edition, was the first turbojet engine to be built and run in the world. Although an experimental engine and not intended for flight, it was designed to be very light by normal engineering standards. The engine had 4 basic components: a single-stage centrifugal compressor with double-sided impeller, a single straight-through combustion chamber, a single-stage, axial flow turbine and a convergent propelling nozzle attached to a jet pipe. The shaft connecting the turbine to the compressor was made as short as possible to avoid whirling. The combustion chamber was connected to the compressor outlet by a very large single spiral duct, giving the engine an asymmetrical appearance. Whittle designed the centrifugal compressor to develop about 4:1 pressure ratio when, as far as he was aware, the best previously demonstrated performance in a single stage was about 2.51. He specified a double-sided impeller to give his required airflow from a smaller diameter impeller than could be obtained from a single-sided one. The smaller impeller allowed a higher turbine speed, which reduced the loading on the single-stage turbine and improved its efficiency. The 16.5 in, 419 mm diameter turbine had to develop 3000 HP, 2,237 kilowatts, to drive the compressor. One disadvantage of a double-sided impeller is the requirement, in an aircraft installation, for an intake with a plenum with its higher pressure losses. A disadvantage for the design of the rotor thrust bearing is no axial load from the impeller to balance that from the turbine. Whittle sought help in designing the combustion system and had visited the British Industries Fair. When he discussed the requirements for his combustion chamber with various exhibitors, he had been practically laughed off every stand until he discovered Laidlaw, Drew and Company, a firm prepared to tackle the difficult problem of combustion at intensities 20x those in refractory-lined industrial applications. By the end of 1936, total expenditure on design and manufacture of the engine amounted to £2,000. Testing of the first model started on the 12th of April, 1937 at Rugby. During the testing, the British Thomson Houston, BTH, chief engineer considered it unwise to exceed 12,000 rpm in the open factory for safety reasons after a run on the 23rd of August up to 13,600 rpm. The 31st and final run was on the 24th of August, 1937. A significantly different, symmetrical design was adopted for the second model. 10 spiral ducts connected the compressor outlet to a single, large, reverse flow combustion chamber, the outlet of which discharged forward through the turbine before turning rearwards to exhaust through 10 jet pipes. Some heat exchange was expected from the exhaust pipes to the 10 ducts delivering air to the combustion chamber, as they were all enclosed by the outer casing. Testing began with a reconstructed engine at the premises of the BTH's redundant Ladywood foundry at nearby Lutterworth in Leicestershire on the 16th of April, 1938 and continued until the turbine was damaged on the 6th of May, 1938. A third reconstructed engine was ready for testing on the 26th of October, 1938. Significant changes were also introduced in the third model. It had 10 reverse flow combustion chambers, giving a similar configuration to that of the later Power Jets W.1 and Power Jets W.2 turbojet engines. This configuration was also adopted for the Rolls-Royce Welland and General Electric J31 jet engines. One advantage of using 10 combustion chambers, smaller by a factor of 1/SQRT10, was they could be more easily be tested on a combustion rig. Owing to a shortage of funds, many of the components would be modified or repaired for testing on later engines. Whittle and his team experienced many problems developing the three models. Compressor and turbine efficiencies and durability were improved. Poor fuel system and combustion performance no longer limited the testing of other parts of the engine. The general design of the follow-on W1 engine was very similar to the third model of the experimental engine. The team demonstrated that the turbojet had the potential to compete with the large reciprocating aero engines then being mass-produced for the UK rearmament programme. The initial rounded bulb de Laval type turbine blade root fixing was later replaced with a new triangular fir tree design after repeated stress/fatigue failures of the earlier type. The fir tree design would be used on all Whittle's subsequent engines. After severe initial combustion problems, in late 1940 a new design of combustion chamber designed by Isaac Lubbock of the Shell Fulham Laboratory was incorporated. This Lubbock chamber /burner proved the answer to many of the combustion problems. The reverse flow type of combustion chamber, as implemented on the third engine, was necessary to allow the continued use of the more expensive components, for example rotor assembly, which had been designed for the completely different straight-through combustion chamber used on the first engine. The reverse flow arrangement had no thermal expansion problems. It allowed the continued use of a very short shaft between the impeller and turbine. The end covers at the rear of the chambers could be easily removed for inspection and modifications to the combustor components. Whittle had assumed the use of vortex flow in the turbine blades, however BTH engineers had not incorporated this and had manufactured the blades with insufficient twist. Whittle's subsequent insistence on this subsequently led to deteriorating relations with BTH engineers. The WU was effectively destroyed by turbine disc failure on the 22nd of February, 1941. Work continued with the Power Jets W.1. Variants, edit. WU first model experimental engine. Initial design with asymmetric spiral duct connecting compressor outlet to single straight-through combustion chamber. First run the 12th of April, 1937. Design data. 1 airflow, (-25.7 pound/s, (11.66 kg/s). 2 shaft speed, 17750 rpm, 296 rev/s. 3 turbine power output, (2950 HP, (2200 kilowatt). 4 compressor impeller diameter, (19.69 in, 500 mm). 5 compressor impeller tip speed, (1525 foot/s, 465 m/s). 6 turbine tip diameter, (15.75 in, 400 mm). 7 turbine tip speed, (1220 foot/s, 372 m/s). WU second model experimental engine. Single reverse flow combustion chamber. First run the 16th of April, 1938. WU third model experimental engine. 10 reverse flow combustion chambers. First run the 26th of October, 1938. Applications, edit. None. Specifications, WU first model design assumptions. Performance not actually achieved, edit. General characteristics. 1 type, centrifugal flow turbojet. 2 length, (67.2 in, 1707 mm, excluding jet pipe. 3 diameter, tilde 45 in, tilde 1143 mm, across compressor. 4 dry weight. Components. 1 compressor, single-stage centrifugal with 19-inch diameter double-sided impeller, diffuser vanes installed part-way through testing, material, aluminium R56. 2 combustors, single straight-through design, located immediately downstream of elbow in spiral pipe. 3 turbine, 14-inch diameter with 66 blades, BTH non-vortex design, single-stage axial flow, with no nozzle guide vanes, material of disc and blades, Firth Vickers stay blade. 4 fuel type, kerosene. Performance. 1 maximum thrust, tilde 1,389 lbf, tilde 6.18 kN. 2 overall pressure ratio, tilde 4.41. 3 air mass flow, tilde 26 pound/s, tilde 11.79 kg/s. 4 turbine inlet temperature, tilde 1434 F, tilde 779 C. 5 specific fuel consumption, 0.942 pound/hour/lbf, tilde 26.69 G/s/kN. See also, edit. 1 Heinkel Hees 1. 2 Power Jets W.1. 3 Power Jets W.2. 4 Rolls-Royce Welland. References, edit.